Alright, so in this video we are going to solve one of the problems or one of the selected exercise of the book Feynman's Tips on Physics, which is a supplement problem book for the Feynman's lectures on physics. In fact, this is the first problem that every reader encounter, or the first selected exercise, which is about statics in mechanics. Or rather, as the title reads, equilibrium of a ball on an inclined plane against a vertical wall. Let us read the problem. 1, which is basically given as the figure of the problem. A ball of radius 3.0 centimeter and weight 1 kilogram rests on a plane tilted at an angle alpha with the horizontal and also touches a vertical wall. Both surfaces have negligible friction. Find the force with which the ball presses on each plane. So we are interested to find or to determine the forces that the wall and the inclined plane exert on the ball, or vice versa. Because according to Newton's third law, which says that every action has an equal but opposite in direction reaction. Okay, so again, this ball also presses or exerts two forces, one for the wall and one for the inclined plane, equal in magnitude as these two surfaces exert on the ball, but in different direction. Okay, so this is not your easy type of inclined problem, which most students expect to draw the diagram as they do naturally. This is a different one, because we will see by the end of the video that the equations that represent these two forces are very different. Okay, so first of all, what I'm going to do, I'm going to assume that, of course, for this ball, most of the mass is concentrated at the center, and I'm going to draw the forces on this ball directly. Okay, so let me just get the first arrow. I suppose the wall exerts a force in this direction exactly, and the ball has also a gravitational, there's a gravitational force acting on the ball, okay? And the normal force for this inclined plane, notice that the wall force could be stated as same as the normal force, but we will call it as wall force, okay, for simplicity's sake. Now the inclined plane also exerts a normal force, which is always perpendicular to the surface. So if we draw it in this way, excuse me, something like this, it's somewhat tilted, as you could see. All right, now if I draw a dashed line here to show you that the normal force is tilted about an angle. All right, now let us get back to the standard. Notice that this angle alpha here is actually equal to this angle here geometrically. All right, same on here too. This is alpha again. So let us just label the direction of the forces. So this is Fw, which means wall force, and this is Fg, the gravitational force acting on the ball, straight downward, and this is Fn, which is the normal force that is perpendicular to the surface of the incline, but it is tilted about this direction, or this dashed line. All right, it's tilted, you could see. So what I mean by tilted, we could basically decompose this normal force into its own components, the vertical component and the horizontal component, which is essential in solving this problem. So the let's say the horizontal part, which is about here. Okay, let me just make it, excuse me, the arrow more clear. So this direction is actually Fn, okay, sine alpha, and this direction, let me just give a direction here. This is Fn cosine of alpha, all right, according to trigonometry, the adjacent part. So now, according to statics in mechanics, or in equilibrium, we say that the sum of all of the vertical direction forces is equal to 0. Similarly, for the x components, or the horizontal parts, are all equal to 0. Because the ball is stopped, all right? There is no movement. It's static. This is a static equilibrium. So, well, that's easy because the force diagram aids us to, implement those directions or this diagram into equations. So for the vertical parts, we could see that easily, that Fn, for this part, let's just write the equations for this part, the y components. We see that positive Fn cosine of alpha minus Fg, because downward, is equal to 0. Okay, so in other words, we have that Fn is equal to what? Well, it's equal to mg divided by cosine of alpha. One could find that. So this is the normal force, or rather, this is the incline force. Okay, or in other words, again, this is the force that the ball exerts on the incline. Okay, this is the first finding. Now, let me delete this. Let's go back to the x component. Okay, so for the x component, it's trivially easy. All right, it's trivially easy to find. We see that positive, of course, we are assuming that the right, or the positive x-axis, this is the positive x-axis, this is the positive y-axis, this is the negative y-axis, and this is the negative x-axis, all right? This is our coordinate system. Notice that. We take right as positive, left as negative, down as negative, up is positive, okay? Do not forget that. So we have positive wall force minus Fn sine alpha is equal to 0. So in other words, we have that Fw is equal to Fn sine of alpha. Now that's not the end. This is equation 1, and let's say this is equation 2. By substituting equation 1 into equation 2, we could finally get the final wall force expression. So let us do that. I'm going to delete all of this and bring equation 2 up somewhere like here. Okay, so let us just substitute it, okay? We get Fw is equal to Fn, which is nothing but mg divided by cosine of alpha multiplied by sine of alpha. Now we know that in trigonometry that sine alpha divided by cosine alpha is nothing but tangent alpha. So we get mg tangent alpha. So this is the wall force. Let me just write it down here. Let's just move it to here. This is nothing but Fw. So this is our final form of the wall force. So we have found the wall force and the incline force, which the ball or the the surfaces exert on each other. It does not matter because equal in magnitude, according to Newton's third law, but different direction, which is already we have calculated both or determined both expressions. Let me just call this a second equation. So this is it for this problem.